We're very happy to have as the first speaker professor at the Institute, Nathan Seiberg, who will tell us about symmetry.
Thank you. Thank you, Igor. Thank you, Chiara. Thank you also, I think, on behalf of everybody, I want to thank Chiara for running this program for so long and so successfully. I personally benefited a lot from these lectures. I sat here in the audience learning things. I see here some faces I recognize, various ages. Some of you have heard me talk about related topics, either in Jerusalem in the winter or in Boulder a few weeks ago. The talks will not be exactly the same. There will be major differences. Well, will not be the opposite, but there will be some overlap, but there will be a lot of, I reorganized it and I emphasized different things. And I thought it would be nice to start this school about very complicated, nonlinear, fancy quantum field theory. We're just discussing quantum mechanics. So what I will do in this lecture is going to a lot of detail through a number of quantum mechanical examples demonstrating a general phenomena. And I'll use fancier language than necessary for these quantum mechanical examples because they're so easy. But so in a way, it would be kind of overkill for the quantum mechanical examples. But personally, I feel that understanding almost trivial examples using fancier language is very good, because once you go to more complicated examples and you get confused, you can always go back to the trivial example, figure out, well, how did it work there? So the topic of my talks, all of them, will be various aspects of symmetries. And this is a huge subject going back centuries, affecting art, architecture, but also physics and mathematics. I will say very little about the architecture and the art in these talks. So what's a symmetry? So I'm going to start with a very limited definition of symmetry, and maybe later in the lectures, you will hear more complicated extensions of these ideas. So a global symmetry means that there's a unitary operator, U. Can you see that in the back? There's this unitary operator U that commutes with a Hamiltonian. Now, this can be extended in various ways. It could also be anti-unitary if we discuss time reversal. We could also discuss other generalizations, but for the moment, we'll just take this definition. So that's the first condition. The second condition is that the operators are in a faithful representation, are in of the symmetry group. What does this mean in plain English? It means that there is no symmetry operator that acts trivially on everything. Why do I add this restriction? Because imagine you thought that the symmetry is SU2, and I think, no, it's SU2 times SO5. But the SO5 doesn't act on anything. Then the SO5 factor is completely trivial. We shouldn't discuss it. We'll see more sophisticated versions of this later. So requirement number one I would like to have is that it's unitary, and then it should also be faithful, and the representation should be linear. So all the operators in linear representation of the symmetry. What does linear mean? It means that it acts like an ordinary representation, not up to phases. This will be very important because I say right now that Wigner taught us that in quantum mechanics, the operators are in a linear representation of the symmetry, but the states can transform in a projective representation of the symmetry. And this projectiveness of the Hilbert space will play a crucial role later. So how does the symmetry act? Every operator O, OI, is mapped to U, OI, U inverse, which is some transformation Rij of U of Oj, sum over J. So that's what it means. We have a unitary operator U. I act on the operators by conjugation, and it maps the operator to a linear combination of other operators in the theory. And the matrix R, which acts, it's a huge matrix that acts on all the operators in the theory, provides a linear, faithful representation of the symmetry group. Every one of these adjectives is crucial for the rest of the talk. Now, this can be generalized in various ways. Some of that you will hear later in these lectures. There would be higher form symmetries, non-invertible symmetries, anti-unitary symmetries, supersymmetry, and so forth. But I'm not going to discuss any of these. I'll just stick to that. And for the purpose of this talk today, I will talk mostly about quantum mechanics. So that's more or less will be it. Later in the lectures, I'll talk about field theory. And then we'll also impose that the operators act on the local operators of the theory. So an ordinary field theory differs from just saying, oh, it's a more complicated quantum mechanics system, because we have the notion of locality. We have the operators are acting at the point, and we would like that when the symmetry acts on them, it maps an operator at the point to another operator at the point, perhaps at a different point, but it maps a local operator to a local operator. Again, recent developments in symmetry go beyond this more limited description of symmetries, but I'm not going to discuss it here. What do we do when we have a symmetry? The modern way of thinking about the symmetries is to pretend that we couple the system to background gauge fields for the symmetry. I emphasize the symmetry is not a gauge symmetry, it's a global symmetry. It acts on the Hilbert space, it acts on the operators, but let's pretend that we have some gauge field, classical gauge field, and we can use it to couple it to the system. So we consider the system not in isolation, but we consider the system as as one point in a family of theories that are labeled by the background gauge field. And we'll see examples of that. But the object of interest, we turn on some gauge fields. So for example, imagine we have a U1 symmetry, and we turn on vector potential for the U1 gauge field. We add a vector potential for U1. It couples to the fields in an obvious way, but we don't integrate over A. A is a classical field. It doesn't have to satisfy any equation of motion. It's an arbitrary prescribed classical field. And then we compute the partition function over all the fields with S depends on A, and we get a functional of A. So we are very powerful. We solve the system and we compute that. We'll do that explicitly in some examples. And then we ask, what happens if we're doing a gauge transformation? AG is the gauge field A transformed by G. Is the partition function gauge invariant? And what typically happens is that even if the symmetry is perfectly good, the partition function is not gauge invariant, but this thing differs by a phase. A phase that depends on the gauge transformation parameter G, and the gauge field A. The next thing we could say, well, maybe we got the action wrong. Maybe we should add some terms to the action to fix it up. So we have worked very hard. We tried to add whatever we can, and we can't get rid of this omega. If that's the case, we say that there's an anomaly. As you can see, this has nothing to do with field theory. This has nothing to do with the infinite number of degrees of freedom. It has nothing to do with the need to regularize the theory. It also has nothing to do with fermions. It has nothing to do with attaching the system to a bulk. In different communities, people have different descriptions of it, but the statement is this minimal thing. And we'll see how it appears in various cases. So the simplest example I'm going to discuss is a single qubit. So this would be example 1. Example 1. 1 qubit. Or equivalently, 2-level system. Or equivalently, 1 fermion, 1 complex fermion in quantum mechanics. Are people familiar with these 3 different presentations of the same system? Who is not familiar with this? Who is? Okay, great. If I'm going too slowly, please slow me down. Please tell me. So what's the global symmetry here? And we can mention several different answers. Just by looking at that, we could say, we have a U1 symmetry that rotates the fermion. That's clearly a symmetry. We could be more sophisticated and say, oh, there's another symmetry. Psi goes to psi dagger. It's like charge conjugation. Together, they give us O2. That's option number 1. Option number 2 is we look at the qubit. We have a 2-dimensional Hilbert space. We can perform any 2-by-2 transformation on it. The Hamiltonian vanishes. All of them commute with the Hamiltonian. So going back here, H is 0. Every 2-by-2 matrix commutes with it. So now somebody might say, no, it's U2. But going back to what I said here, is that the symmetry is the group that acts linearly on the operators. Or alternatively, in quantum mechanics, the wave function is a ray, is not a vector. So we should mod everything out by an overall U1 phase. So the symmetry group is really this one, which is the same as SO3. Notice that the Lagrangian that I wrote here, which exhibits only O2, it's a subgroup of SO3. So it's often the case that the Lagrangian does not exhibit, the classical Lagrangian does not exhibit all the symmetries of the system. The symmetry of the system is SO3, but the Lagrangian exhibits only a subgroup O2. This phenomenon, the fact that the symmetry could be bigger here, the symmetry is bigger, is known as a quantum symmetry. So in this case, this is an example of something I said earlier. In this case, it's clearly overkill. We have this stupid 2-level system. What am I talking about? Quantum symmetries. It is what it is, and we shouldn't think too much about it. But well, we should think too much about it. But that aspect of being a quantum symmetry might look like just using too fancy a language. But this is actually very helpful to identify the symmetries. The O2 subgroup acts on the operators made out of psi and psi dagger, but there's actually a larger symmetry, SO3, that acts on the Hilbert space. And I leave it as an exercise for you to write the 3 different generators of SO3, JX, JY, and JZ, and express them in terms of the fundamental fermions. So you can take it as an exercise. But I emphasize that the symmetries act linearly on all the operators in the theory, but it acts in this case projectively on the Hilbert space. So let's do that in a little bit more detail. We have a symmetry operator S. It depends on a vector, R, and we can write it as e to the I, R vector, thus S vector, and S vector is sigma matrices with a half. And I forgot the equal sign. So this is how the SU2 is realized on the Hilbert space. And if we have a group, the group is SO3. and things act by conjugation, we could ask ourselves, what are the conjugacy classes of SO3? So we can limit ourselves to group element that depends on the real parameter Xc, and write e to the I Xc Sz. So whatever we do in SO3, we can say that this is a rotation, but the rotation is only around the Z axis by an angle Xc. And it should be such that G of Xc is conjugate to G of minus Xc. Who can tell me why? Why is it rotation by Xc is the same as rotation by minus Xc? It's not the same rotation. Thank you. It's because they're conjugate to each other. I'm only writing the different conjugacy classes, and a rotation by Xc is conjugate to rotation by minus Xc. So they're conjugate to each other. And also important for our purposes is that Xc plus 2 pi is not the same as G of Xc. This equation is crucial for us. So in SO3, if I do a 2 pi rotation, I come back to where I started. So as SO3 elements, this is a triviality, the fact that I have a plus here, and the fact that these two are conjugate to each other needs a little bit more work. These are properties of SO3. But the way they act on the Hilbert space is different, because here we have a minus sign. The minus sign is there because the group that is realized on the Hilbert space is not SO3, but it's double cover SU2. And then when we perform a 2 pi rotation, we come back to where we started in SO3, but it's not the same point in SU2. So why am I saying that the symmetry is SO3 rather than SU2? Because I'm looking at this equation, which tells me how operators transform. Operators transform by conjugation. The Hilbert space transformed by acting with the operator on the state, but the operators transform by conjugation. And if I look at the action of this G, I put it both on the left and on the right on every operator, and I compare Xc and Xc plus 2 pi, the minus signs cancel, and we are left with the same action on operators. So the group element G of Xc and the operator G of Xc and G of Xc plus 2 pi are not exactly the same operator. They differ by a minus sign, but the way they act on operators is the same. Questions so far? So the Hilbert space is in a projective representation, but the Hilbert space is in a projective representations, but the operators transform linearly. Now let me describe it as an anomaly. So I gave a definition of an anomaly. I said, whenever we have a global symmetry, we take classical background fields, we couple it to the system, and we compute the partition function. So what do? We take a gauge field A. It's a gauge field of SO3. So the symmetry is SO3. I take some gauge field. We are in quantum mechanics, so the gauge field has only a time component, does not have a space component. And we can actually pick a gauge such that the gauge field is independent of where we are in time, more precisely in Euclidean time. So what having a gauge field means is like acting with an operator on the Hilbert space. So the partition function I mentioned earlier, that depends on the gauge field, depends only on the parameter Xc, which is trace e to the minus beta h times G of Xc. So space-time is a Euclidean time circle with periodic boundary conditions. So we evolve up to beta, then we act with the operator G of Xc, and then we evaluate the trace. This is the same as computing the partition function with the background gauge field. So fortunately, it's not too difficult to do the calculation. H is 0. So we don't need to worry about that. So what we have is a trace, and G is very similar, very simple. I wrote it here in terms of SZ. So I have two states. One of them has e to the I psi xc over 2, and the other has e to the minus xc over 2. So we get 2 cosine xc over 2. So this is the partition function. So we evaluated this partition function. It's an example of what I wrote up there. And now we can check what omega is. So first we say xc should be the same as minus xc. Xc should be the same as minus xc. So this thing works. But z of xc plus 2 pi is minus z of xc. So this minus sign that we have here is this e to the minus I omega that I wrote up there. So there is a minus sign here. The partition function at xc is not the same as the partition function at xc plus 2 pi. They're not the same. Even though the symmetry is SO3, and even though xc as a parameter should take values on a circle where xc is identified with xc plus 2 pi. Now, somebody could say, wait a minute, instead of g of xc, let me say g of xc, which is, so g of xc was e to the I xc sz. So somebody could say, let's change it and put instead e to the I xc sz plus a half. So we could do that, and we can repeat the same computation. And if we do that, we no longer have the minus sign here, because under the new SZ, the two states do not have charges plus or minus a half, but have charges 0 and 1. We'll see more examples of that later. Okay, that's wonderful. We get rid of this minus sign here. What's wrong with this? The previous equation, I messed up this one. So I can mess up this one or that one. I have the freedom to move where the quote unquote mistake is, but I cannot get rid of the problem completely. Such a redefinition of the operators, or if you wish, of the action, is usually referred to as adding a counter term. So we usually hear the phrase adding a counter term in more complicated settings. We have divergences in quantum field theory. You need to subtract the divergences. You don't need any divergences. This is an example of adding a counter term. And the freedom in moving the anomaly around is a freedom in adding counter terms. This is common in quantum mechanics. When you want to define quantum mechanical operators, there are a lot of ambiguities, normal ordering ambiguities, multiplying it by various phases, etc. This is one of them. And it's up to us to decide how we want to do that. In this case, we would like to satisfy the full SO3 symmetry, but we can't. So questions about example number 1. The full symmetry is SO3. The full symmetry, that's very good that you asked. Thank you. By the way, I have experience with this lecture hall. It's terrible. The fact that I stayed here makes people feel different, far away from the speaker, and they do not ask many questions. I can give the same talk here in a regular lecture hall, and the number of questions is different. So please, please ask questions. And once we are at it, I'm around all week. You can also grab me anywhere around, and I'll be more than happy to answer questions, either about the talks or about other things. I cleared my schedule in your honor for these 2 weeks. So this is example 1. And I'd like to move now to example number 2. And it will also have an anomaly of a somewhat different flavor. And we'll see the connection between the 2 examples. I'm still in quantum mechanics. And so this would be example 2. And that's a rotor. So we start with the Lagrangian. It's a half q dot square plus theta over 2 pi q dot. And q is identified with q plus 2 pi. And it measures the position of a particle moving on a circle. Who has never seen this example? Okay, that's great. So what's the global symmetry? First, we have U1, which maps Q to Q plus alpha. And it's U1 rather than R because Q is circle valued, and so is alpha. We also have a Z2 symmetry, Q to minus Q. But this term is invariant, but this term is non-invariant. So we have that symmetry only for theta being 0 mod pi. So when theta is 0, it's obviously a symmetry. And when theta is a multiple of 2, theta is 2 pi periodic. The physics at theta is the same as the physics at theta plus 2 pi. So that would be with the 2 here. But also when theta is pi mod 2 pi, this term flips sign, but then I use the fact that theta is the same as minus theta to show that that's also a symmetry of the problem. Okay, so let's talk about theta equals 0 mod pi. So we have a U1 and we have a Z2. What symmetry do they combine into? That's right. They combined into O2, which is the semi-direct product of U1 and Z2. So the Z2 acts on the U1. So let me work out some elementary quantum mechanics. What's the momentum? The momentum is the derivative of the Lagrangian with respect to Q dot. So that's Q dot plus theta over 2 pi. And the Hamiltonian is found by writing PQ dot minus the Lagrangian and expressing it in terms of P. So we get a half P minus theta over 2 pi 180 square. So that's easy. And the eigenvalues of the operator P must be integers. Why? Because Q is circle valued. So the wave function is e to the I Q, e to the 2I Q, etc. And then P, which acts as d by dq, always gives an integer. So we know the spectrum of the Hamiltonian. Square. And I really love this spectrum, so I'd like to plot it. So this is 0, this is 2 pi, this is 4 pi, this is pi, this is 3 pi. So notice that at pi and at 3 pi, we have degenerate states. Why do we have a degeneracy at theta equals pi? Let's go after the symmetry. So we said that we have a U1 symmetry that acts as U1 maps Q to Q plus alpha. And we also have a Z2 symmetry, which I'll write as R. The generator is R. First. So Q goes to that, which is minus Q. So now let's see how R acts on the charge, the U1 charge Q. So the charge here is the same as the momentum we had before. So R flips the sign of this, but it doesn't touch the same number. So what we have here is minus q dot plus theta, which is minus the charge plus twice theta over 2 pi. So for theta equals 0, no problem. We have the symmetry. For theta equals 2 pi, I can redefine P, redefine the charge to be the charge minus theta over 2 pi. And then I will get rid of this guy. But when theta is a multiple of pi, I don't have the Z2 symmetry. That clear? So for theta multiple of pi, I can perform this redefinition. But then you see that I'm in trouble. And I can see the trouble two different ways. If I do this redefinition for theta equals pi, then R acts properly. Q goes to minus Q. However, the eigenvalues of the charge are no longer integers. The eigenvalues of the charge are half integer. Alternatively, I could keep the original definition, and then the eigenvalues of the charge are integer, but R does not flip the sign of the charge. Let's see it here in this plot. This curve corresponds to the state with n equals 0. This curve corresponds to the state with n equals 1. So this parabola. This parabola corresponds to the states with n equals 2. So we see that here we have two degenerate states. Can you see here? So we have two degenerate states with n equals 0 and 1. That's not how the Z2 we want act. We wanted the Z2 to flip the sign of the charge. Right? Want to take Q to minus Q. This is how the group O2 acts. But we have two states with charges 0 and 1, and the Z2 doesn't act between them. So somebody could say, well, you misidentified the charge. It's really plus a half and minus a half, and then the Z2 acts well by flipping the charge. However, then the charge is not quantized. So we have this dichotomy here. Either the charge is always an integer, and then we don't realize the Z2, or the charge can be half integer, plus or minus a half. We see the Z2, but the charge is not realized correctly because the charges are half integer. This is the statement that the O2 global symmetry is realized projectively. I mentioned we can think of this problem as one Dirac fermion. Was somewhere here, maybe here. No. Well, in one of these blackboards, the model was represented. I don't know where it's gone. The model was represented as one Dirac fermion. And how do we quantize the Dirac fermion? We say it's a creation and annihilation operators, and there's an obvious U1 that rotates the fermion by a phase. And then there's a standard thing. We have two states. Either one of them has charge 0 and the other has charge 1. Then the charge is realized properly, but charge conjugation does not act simply. Or we say the charges of the two states are plus or minus a half, and the charge conjugation is realized properly, but the U1 is not. So before we headed to the two-level system, oh, here it is. Here is the fermion. That was at the two-level system. Now we see it here in another system, which doesn't even have fermions, has an infinite dimensional Hilbert space. And we see it around here for the states near theta equals pi. Since I would like to discuss anomalies, I would like to discuss this phenomenon in terms of anomalies. So how do we think of it as an anomaly? One way is just to say that for theta equals pi, for theta equals 0 or 0 mod 2 pi, The symmetry is O2. There's no anomaly, but for theta equals pi mod 2 pi, the symmetry is still O2, but it is realized projectively, and that means that there is an anomaly. Let's describe that in terms of gauge fields. This system is nice because it's exactly solvable. So I turn on background gauge field, and then the Lagrangian could be a half q dot plus a, quantity square, plus theta over 2 pi. Before we had q dot, so now we write q dot plus a so that it is gauge invariant. And we can also add an integer times a. This integer times a, again, in the spirit of using fancier language for simple things, the simple way to say that is that we shift what we mean by charge by an integer. The fancier way to say that is that this is a Chern-Simons term. In quantum mechanics. Okay, so once we add the gauge field, we have freedom in adding such a term, and you'll soon see why this term is important. So we can still think of this A. So imagine A is constant for simplicity. We can always choose such a gauge. And we can again find the Hamiltonian and the states and so forth as a function of A. But we're interested in computing the partition function and see how it depends on A. So I'm setting theta to be pi. And I'm going to Euclidean space. So e to the I, the only gauge invariant information is this phase, e to the IXC. And now I can try and compute the partition function as a function of this background field. So I'm only at theta, I'm setting theta equals pi. Theta equals pi, I'm not writing it, and I'm just computing the partition function. Trace e to the minus beta h. And then we have from this charge, from this background gauge field C, we have here n plus k. But since we already diagonalized the Hamiltonian, we know what it is. It is sum over n from minus infinity to infinity, e to the minus beta over 2. In general, there's a theta, but I'm just putting theta equals pi, so we get that minus a half square e to the IXC n plus k. So this is the partition function. This function has a name. It's some theta function. That's not important for what I'm going to say. So we evaluated the partition function. Beta is the inverse temperature or the length of the Euclidean circle. And Xi is the background gauge field. So now let's check its properties. It's actually going to be very similar to this. Oh, I don't want to do that because I will need it. So z of Xi plus 2 pi. So n is an integer, k is an integer. So this is a good phase. So Xi is the same as Xi plus 2 pi. However, z of Xi of minus Xi is not equal to z of Xi. Instead, what I find is that z of Xi multiplied by e to the minus I 2k plus 1 Xi. So when Xi flips sign, the partition function acquires a phase that depends on the background gauge field Xi. That's the anomaly. So what do we have here? The U1 is proper, but the Z2 is not realized properly. So that means that the U1 is okay, but this means that the Z2 does not work. So what are we going to do about it? We have several options. All of them are standard in various physical problems. And let me go through all of them. There's no right option or wrong options. All the options are correct. And for certain purposes, one option is better than the other. So option one, as is. That's what we found. That's the answer. The U1 is properly normalized. All the charges are quantized. The Z2 is not quite there. It's almost there. The anomaly is entirely in the Z2. It is what it is. Or in other words, K is an integer. Option two, set K equals -1/2. We set K equals -1/2. The Z2 is good, but now the U1 is not. Notice it's the same story as before in the two-level system, for reasons that I will soon explain. The Z2, with this choice, we would say that the two states that are degenerate have charges plus and -1/2, and then at higher levels, they have other values of the charge, but such that the Z2 always works, but the U1 is not because the charges are half integers. There's a third option, set K equals 0, and add a bulk. And at the bulk, write e to the I theta over 2 pi, integral of f, two-dimensional integral of f, where this is f, this f is the f of the A that I had before. So I extended system, which had only time. This is time. So I'm adding a bulk. I'm adding a one-dimensional space attached to that line. But there's nothing in this bulk. The bulk has only classical gauge fields. And what the classical gauge fields do for me is to keep track of the various symmetries. In condensed matter physics, this is called SPT, symmetry protected topological phase. The system in the bulk is almost trivial. It's almost trivial. It's trivial in the sense that there are no degrees of freedom there, but it's only almost trivial because it has this dependence on f, so that even if we set theta equals pi, it is e to the I 1/2 integral of f. And since it has the 1/2 here, it means that if I change the way I extend A to the bulk, the integral of f could shift by 2 pi, and this guy could flip sign. And this sign is all we are talking about here, these various signs under the parity transformation. So we have these three options. All of them are correct. And all of them amount to changing the counter term or adding these bulk terms. Most of the dynamics is unaffected by these choices. So now I'm going to do something which is not often done in quantum mechanics, and that is to go to the low energy field theory or to the low energy theory. Yes. I can put K whatever I want. It will just shift the, I could put K whatever I want, and the Z2 will act differently. This is like, you see, the charge is the derivative of the Lagrangian with respect to A. So changing K is like adding a constant to the charge. So your charge could differ from mine by 7. There's nothing wrong with that. That might not be a convenient thing to do if we would like to preserve the Z2. But if we don't care about the Z2, but we care that it's U1, so we are allowed to shift the charge by an integer. Okay, so now I'd like to focus on the low energy theory. What did I do? So I'm now a low energy person, looking only at the low lying states. This is something we'll do later when we discuss field theory, we'll discuss the low energy effective field theory. But in this case, we'll just do it in quantum mechanics. So we have an infinite number of states in the Hilbert space that I outlined here. And we are only interested in the low-lying states. So if I'm theta equals 0, there's only one state. There isn't much I can say. And that's also true for generic theta. But at theta equals pi, we have two states. But if theta is near pi, they're nearly degenerate. If theta is exactly pi, the two states are degenerate. And I would like to focus only on these states. How do I focus on the low-lying states? I'm going to very low energies. I'm only talking about very low-lying excitations. I do not use a lot of energy that would kick the system to higher energy states. So I'm focusing on these low-lying states. And the way to do that in terms of the partition function is simply to take beta to be large. So I had this partition function. So I'm going to focus on the low-lying state by taking beta large. When beta is large, all the states here, all the terms in the sum are exponentially suppressed. And the lowest ones are the ones where this is minimum. So this happens when n is 0 or 1. So when I focus on the low-lying states, I take beta to infinity. And I have only two terms in the sum. And they give me a partition function goes to e to the minus beta over 8 e to the I ck 1 plus e to the I c. This is the partition function. And now we can substitute various values of k and see what we get. And we can go through the three options I mentioned before, where the three options are giving k an integer. So for example, 0, k is 0. And then we have something, c is the same as c plus 2 pi, but c is not the same as minus c. I can also set k to be minus a half, then c is the same as minus c, but shifting c by 2 pi is not the same system. Have we heard this story before? Yes, that's exactly the two-level system we discussed earlier. And that's not surprising, because what we have here is two levels. So what we see here is that if we take the rotor and look at theta equals pi, there are two low-lying states. There are two low-lying states in the spectrum. They realize O2 projectively, and the low-energy system is exactly the same as the low-energy system we discussed earlier in this lecture. There's one crucial difference between them. The full system, or the rotor, has O2 symmetry. But the two-level system, or the qubit, has SO3 symmetry. So what do we see here? We see that the full system, which we can say UV. So in the UV, I see all the high energy states, I see everything. The symmetry is O2. But the low energy person, it's the IR, sees SO3 symmetry. This is a general statement. Whenever we have a system at high energies and at low energies, the symmetries don't have to be exactly the same. At short distances, we have some symmetry group GUV. How much time do I still have? Half an hour, great. So when did I start actually? Okay, I'll go half an hour. Okay, half an hour, that's good. So at short distances, we have some symmetry group GUV, which is the symmetry of the full system. At low energies, we have GIR, which is the symmetry of the low energy theory. Every symmetry operator in the UV satisfies these requirements over there, is a good symmetry operator in the IR. And therefore, every operator here is mapped to an operator here. However, this map might not be so trivial. it might not be so trivial because some symmetries in the UV might act trivially in the IR. We saw an example of that in the rotor. If theta is 0, the low energy observer says there's only one state in my Hilbert space, just the ground state. Nothing acts there. All the O2 that we had doesn't act. That's the kernel of this map. So this map can have a kernel, all the operators here that are mapped to a trivial operator here. But we can also have new symmetries in the IR that are not present in the UV. So at theta equals pi, we had here O2, which was also realized projectively. And here we had SO3. The name for that, when the symmetry is bigger, is known as an emergent symmetry. This term is more common in condensed matter physics, or accidental symmetry. Which is more common in high energy physics. Same thing. So when we have a new symmetry in the IR that is not present in the UV, we call it an emergent symmetry. It's a symmetry that is not there in the UV. The low energy observer sees it. And here we see a very vivid example of it. The system has O2 symmetry, but the low energy observer doesn't see that the symmetry is O2. And the low energy observer, who does not have access to the higher energy states, sees the two states, they are degenerate, and he or she says the symmetry is SO3. Question. Okay, so you're making it a much more, you put a lot more input that I didn't have here. So for one thing, I have only one parameter here, beta. And when we discuss modular transformations, there's another parameter, because there's tau, which is complex. Later in the lectures, we'll discuss field theories in 1+1 dimensions, and then you have the opportunity to ask the question again. But here, this is the function, and we can indeed perform Poisson resummation of that and do all sorts of fun things with this system. But that's not the direction I would like to go. Yeah. Which one top? Because there are many things here which are. You're talking about this one? Yes. Good question. Good question. So let me say it more precisely. Xi, as it appears here, is a real number. And the partition function depends on the real number, no problem. But now we realize that as a real number, Xi is the same as minus Xi. That's a statement that it is an even function. But it's not periodic because there's a minus sign. So we would like Xi to be a function on the parameter space. The parameter space is a circle, Xi, modded out by Z2. So the parameter space, as we start, Xi is a circle. We also mod out by Z2, so it's like a line segment. We would like Z, the partition function, to be a function. Namely, every point in Xi, we get a Z of Xi. That's what we would like. But we can't do that. So even though the parameter space is a segment, the partition function is not a function of the segment. Using fancier language, it's a section of a line bundle over the space. And this minus sign reflects that. Did I answer your question? This is Xi plus 2 pi, and this is minus Z of Xi. What's it? 0. I will not be able to do it in real time, but Look, the function is 2 cosine xi over 2. Yeah, 2 cosine xi over 2. And I think it would be, yeah, it's 0. Because xi tells us what weight we give to the two states, depending on their charges. So the two states cancel each other. So this is not it's a partition function where the states come with the weight given by the charges. We also see here, yeah. Excellent question. Really excellent question. The way I described it here, using a Hamiltonian formulation with just matrices acting on the Hilbert space, the answer is no. But if I write an effective Lagrangian with time derivatives, there are higher derivative terms that reflect that. And more pragmatically, you compute correlation functions. So if you look, say, at the 2-point function of e to the iq, which is one of the operators in this rotor quantum mechanics, and if I'm a low energy person, that would say it takes one state to the other and it gives 0 on the other state. If I'm a high energy person, I would say, no, it takes me to a state at a higher energy. And then if I compute the 2-point function, I have states that go in between. And they will be suppressed because they are at higher energies as I separate the energies. But this is the experiment I will have to do. This is very good because we are soon going to see examples where what I've just said will be incorrect. But in this case, that's the answer. I think the reason you asked is that in the Hamiltonian, which are matrices acting on these two states, you can't see that. But if you look at it more broadly, the answer is that you can. In the examples that I will have later, even if you look at it more broadly, you cannot. But this would be kind of a... There's another thing that we can see here, which is kind of amusing. It's one of these overkill things. So the system has an O2 symmetry in the UV, and it has an anomaly. And the anomaly guaranteed that every state is degenerate. All the states in the Hilbert space are in a projective representation of O2. That's point number one. So when we have an anomaly in that O2, all the states have to be in a projective representation. And the projectiveness has to be the same. Why? Because the operators are in good representation, in linear representations of O2. So if I take a state in some representation of O2 and act with an operator, the projectiveness of the new state should be the same. This minus sign is an overall minus sign of the whole Hilbert space, not just one state. And therefore, every state is twofold degenerate in the rotor at theta equals pi. You can easily check it. Explicitly, all the states are twofold degenerate. That's the UV person. The IR person says, maybe I can't even solve the system, but I know a priori that every state has to be twofold degenerate. And therefore, the ground state should also be twofold degenerate. This sounds completely trivial, what I've just said. If all the states are twofold degenerate, of course, the ground state is one of them. But in other cases, the statement is not so easy to state. And the way things match between the UV and the IR are not as trivial. And the more general way to say that is that the UV system has an anomaly, and the IR system must have exactly the same anomaly. And that's known as a 't Hooft anomaly matching. So the anomaly as computed in the UV must be the same in the IR. In this case, it was relatively easy because we just solved the system. And that's a general rule about symmetries and anomalies. If you can solve the system, you don't care about the symmetries because you know the answer. What else would you like? But when there are situations that are more complicated where you cannot solve the system analytically, then these are good guides. So let me give an example before I finish this topic. Let's add, take the rotor. So we had a half q dot square plus theta over 2 pi q dot minus v of q. And let v of q be invariant under the Z2 and also invariant under q plus pi, not 2 pi. For example, V of Q is cosine 2Q plus 5.4 cosine 4Q. Take anything Fourier series with 2Q. What happens to the symmetry? So first of all, I don't know how to solve that in general. It's much more complicated. I do not know how to diagonalize the Hamiltonian. But what's the symmetry? For theta equals pi, both for theta equals 0 and for theta equals pi, the symmetry is Z2 times Z2. One of them takes Q to minus Q, and the other takes Q to Q plus pi. And of course, Q is identified with Q plus 2 pi. So the symmetry is Z2 times Z2, much less than the O2 that we had before. And for theta equals 0, the story is as before, and there's no anomaly. But for theta equals pi, there's an anomaly between these two Z2s. So the Hilbert space must realize this Z2 times Z2 projectively, and hence all the so one way to do that is you just say that there's a sigma x and sigma y. They realize every one of them squares to 1, and the product of them, they do not commute, they anti-commute. So this is how the Hilbert space is realized on these two-dimensional representations. So every state is twofold degenerate as a result of this anomaly. That's the UV person. The IR person says, I have to diagonalize the Hamiltonian. I don't know how to do that. That's very difficult. But I know that the ground state will not be unique. The ground state cannot be unique because it has to realize this Z2 times Z2 projectively. So this is an example where we have a system that we can't solve, but we can use the anomaly to know that whatever happens for theta equals pi, the ground state of this complicated Hamiltonian with this particular potential has to be twofold degenerate. Any questions before I change topic? Yes, it's the group is that. So it's Z2 times Z2. So I gave a realization of it. So let this Z2 generated by A and this Z2 generated by B. So the fact that it's Z2 times Z2 tells us that A square equals B square equals 1. But the projective representation means that AB is minus BA. This algebra is also known as clock and shift. It has all sorts of different names. The Heisenberg algebra, there are many different names to this algebra. It's a projective representation of Z2 times Z2. So we know that this is the algebra that has to be realized. So as a group, the way the A and B, the generators, act on operators, they act by conjugation. It acts as Z2 times Z2. On the Hilbert space, this is still true, but there's another minus sign here. That's the way it acts on the Hilbert space. If we conjugate things, this minus sign drops out. So now there's a question in algebra. Find two matrices, A and B, satisfying this algebra. Take it as an exercise, but the answer is here, up to conjugation. You can also take sigma x and sigma z. So all the representations, the representations that realize that are two-dimensional. There's no one-dimensional representation. Let me prove that there's no one-dimensional representation. I can do that. I can solve this one by saying that A is plus or minus 1. I can solve this one by say B is plus or minus 1, but then I'm stuck here. So there's no one-dimensional representation. And yeah, there's huge literature on groups and projective representation. They're classifying by group cohomology, etc., but I'm trying not to get into it. Yeah, so I'm glad you asked because it's really very important. So I'll say it again in a slightly different way. If we don't turn on any background fields, there is nothing wrong with the symmetry. The partition function is invariant if you compute some correlation function of something, and I compute the correlation functions of the things rotated by the symmetry, then we're going to get the same answer. That's a statement that there is a symmetry. So the symmetry is there. Where is it there? When I try to turn on these background fields. When I'm trying to compare what happens with these different operators that should be identified. So naively, if I have two operators that should be identified, I should get the same answer. But they are identified as far as their action on the operators, but they're not identified as far as their action on the Hilbert space. And therefore, they are not identified when I compute the partition function. So the partition function allows me to compute something that I cannot just see easily from how the symmetry acts on the operators. It reflects the operator algebra, but I don't just see it by the way the operators transform under the symmetry. And the fact is that we have some parameters in our problem. The system is the partition function should be a function of these parameters, but it's not. Because xi and xi plus 2 pi should be the same point, but it's not because the way I defined the operator, it was not the same. There's a minus sign between them. Or I could fix that one and define the operator such as xi and xi plus 2 pi would be the same, but then xi and minus xi were not the same. So if I just look at the form of the operator, I see that I cannot satisfy all these things. If I see how the operator acts on the Hilbert space, I see that various points that different values of xi that would correspond to the same operator are not the same. And I can also see that in the partition function. And hence, a partition function is not a function. It is a function on a bigger space. Yes. Yeah, it's the same. So far, it's the same thing. Yeah. No, yeah, it's when you go higher up in dimensions, this will not be true. But so far, the two statements are the same because what does the projective action on the state means? I multiply some operators. Naively, I should get one answer, but in fact, I get the answer up to a phase. That's the projective action. What I do in the partition function, I compute a trace, and that phase is pulled out. Now, if you just think about operators and how they act, sorry, the operators how they act, you might find it easier to think about that this way. There are many reasons why it's easier to think about it in terms of the partition function, because then you don't have operators, you don't need to worry about ordering, just as some function, there is a phase that appears out front. But this is a question of taste. This is just a question of taste. Now, as we go higher up in dimensions, which would be in exactly 1 minute, this will no longer be the case. And the anomaly could be more sophisticated, where you don't see that, strictly speaking, as the action on the naive Hilbert space. You might see it as a projective representation on some twisted Hilbert space, but not in the naive Hilbert space.
From the physics, theta equals pi is 1 unit of through a ray.
It's a half. Well, depending on what your units are, but in the unit of Dirac, this is a half. So you can think of it physically as you have a charged particle on the ring and you put magnetic flux through. So for theta equals 2 pi, this is exactly the one that satisfies Dirac quantization. So if you exactly satisfy Dirac quantization, you can't see that the flux is there, and that's theta equals 2 pi. Theta equals pi is half of that. But the theta equals pi is interesting because pi is the same as minus pi. And that's why you have this Z2 action. I didn't hear the beginning of what you said. I didn't use the phrase operator state correspondence. I was very careful not to use it, and I'm glad you brought it up, because in quantum mechanics, there's no operator state correspondence. There's operator state correspondence in the next topic I'll talk about, but which is 1+1 dimensional field theory. And even then, it might be more subtle. In quantum mechanics, we have a Hilbert space, and there are operators. For example, we talked about the qubit. There are two states and various linear combinations of them, and there are various operators. No, there's no subtlety. There's no reason to translate them in the first place. You can say that you declare that one of them to be trivial, state spin up, and then every operator maps to something, prevents a space. This is a map from an operator to a state, but I'm going to have a different map because I'll take my starting point to be different and go back, but there's no way to go back. There's no way to assign a state to an operator. Yeah, yes, I can make it a lot more complicated in many ways, but I'm talking here about the two-level system. And, well, this was a more fancy example with the rotor. Now, what you said is, of course, correct. But that's because you have the other state around, which gives you the reference. In the example I gave him, you pick a state, and then you can map every operator to the state obtained by acting with this operator on the preferred state, but there's no way to go back. Right? Excellent. So imagine I didn't identify the full symmetry group, but I did identify a subgroup of it. Then I would couple to background gauge fields of that symmetry, and I will learn some things, but I will not get the full power of the symmetry because I missed the rest. Another way of saying it is that I can still deform my Hamiltonian or the Lagrangian, breaking the big symmetry that I didn't know was there, but preserving the subgroup that you noticed. So what I will get would be correct statements about the more general problem, but not the specific problem with the more symmetry. I should emphasize the converse of that. You can also misidentify the symmetry by by finding not a subgroup, but identifying a multiple cover, or which I meant not performing the appropriate quotient. And that was the example before when I said that the symmetry is SO3 rather than SU2. So in terms of SU2, there was no anomaly. The anomaly was only because the symmetry was SO3. So it was very important to identify the proper symmetry, and I had some conditions before. It has to be in a faithful representation. Faithful and linear representation. I think I had the word linear there somewhere. It has to be faithful and linear. So if I say that the symmetry is SU2 instead of SO3, it's not faithful, because there's something that I thought is a symmetry, this -1, but it doesn't act on the operators. If you just, and you know the Hamiltonian? Well, in principle, yeah, you diagonalize the Hamiltonian, you do it analytically, or you put it on the computer, and you get the answer exists. Now, it might be complicated to do it explicitly. And I think one of the goals of this school is for you to be able to solve QCD. Yes, the answer is there. The answer is there, but you might not be able to do it this afternoon. It might take you longer. But no, there's a unique answer. The question has an answer. And you can put it on the computer. 3 more minutes? Okay, so we can move to higher dimensions. I'll first ask, how many of you studied the C=1 compact boson in one form or another? Who never heard of it? one person. Okay, so I'll give a lightning review of it next time, and then we'll see some surprises. I think it's. Thank you.